In this section, let's look at multivariable linear systems. For example, systems that have 3 equations and 3 unknowns. In particular, we want to learn how to put them in row echelon form and then be able to do back substitution. Let's check out this example. You see the original form, you see the row echelon form. When we can get it into that form on the right, then it's real easy to back substitute and find that our solution is an ordered triple 1 minus 1, 2. Stop the video and check that out. This second system is said to be in row echelon form, which means that it has a stair-step pattern with leading coefficients of 1. This is a much easier way to solve 3 equations in 3 unknowns than the somewhat haphazard method that we have often used. This is called Gaussian Elimination. To solve a system that's not in row echelon form, we're going to first convert it to row echelon form. A Gaussian elimination is named after Carl Friedrich Gauss, who I'm sure you've heard of. He's very well known in mathematics. All right, remember there are 3 row operations that we can do. We can interchange 2 equations. We can multiply one of the equations by a non-zero constant, and we can add a multiple of one equation to another. The goal is to use elementary row operations on a system. So check out this system. 2x plus 4y plus z equals 1, x minus 2y minus 3z equals 2, and x plus y minus z equals minus 1. The first equation needs to be 1x, so let's interchange equations 1 and 2. When we interchange them, remember we still have an equivalent system, and so we're good to go. Step 2. Let's multiply equation 1 by negative 2 and add it to equation 2. Okay, that'll be minus 2x plus 4y plus 6z equals minus 4. 2x plus 4y plus z equals 1. And we get 8y plus 7z equals minus 3. All right, this is our new equation 2. So we'll go back over, we'll write down what we have. X minus 2y minus 3z equals 2. 8y plus 2z equals minus 3. And x plus y minus z equals minus 1. Step 3, we're going to multiply equation 1 by negative 1 and add it to equation 3. All right, so we get minus x plus 2y plus 3z equals minus 2, x plus y minus z equals minus 1, and we get 3y plus 2z equals minus 3. So we write our equations down again. 8y plus 2z equals minus 3, 3y plus 2z equals minus 3. And then we notice, okay, I think there's a mistake. Yeah, I didn't copy right. That should have been 8y plus 7z equals minus 3. So I think we've got all the errors fixed now. The next step is going to be to multiply equation 2 by 1/8 because we would like to get 1y. So when we multiply by 1/8, we get y plus 7/8 z equals minus 3/8. Our third equation at this point is still 3y plus 2z equals minus 3. All right, now what do we want to do? We want to get a 1 where that 3, or a 0 rather, where that 3y is sitting. So we're going to multiply equation 2 by minus 3, add it to equation 3. Now here you have to be careful with your arithmetic because we're working with fractions. So we get 3y plus 2z equals minus 3. We add them together very carefully. Minus 5/8 z equals minus 15/8. So we get x minus 2y minus 3z equals 2. Y plus 7/8 z equals minus 3/8. Minus 5/8 z equals minus 15/8. Now we want to take that third equation and get it to be 1z. So we're going to multiply equation 3 by minus 8/5, because minus 8/5 times minus 5/8 is going to get us a 1. All right, so we have x minus 2y minus 3z equals 2, y plus 7/8 z equals minus 3/8, and z equals 3. Now, we're ready to do our back substitution. All right, we know that z equals 3, so y plus 3 times 7/8 has to equal minus 3/8, or y equals minus 24/8, so y equals minus 3. Now we can go back and get x. X minus 2 times our y minus 3 times our z. Do the arithmetic properly. So our solution is the ordered triple, 5 minus 3, 3. Okay, let's try another one and do some of the work in our heads. All right, first of all, the very first equation had a 1. Okay, so the next thing we're going to do is multiply the first equation by minus 1 and add it to the second equation. And then just write down the third equation because it didn't have an x to start with. So we now have x plus y plus z equals 3, minus 3y plus 3z equals 2. And now let's add the second and third equation together. And notice what we get now. X plus y plus z equals 3, minus 3y. Oh, why don't we go ahead and divide by minus 3 and get a 1? We're in good shape. Divide by 7, we get z equals 1. Back substitute. Y minus 1 equals minus 2/3. So y equals 1/3. And now back substitute to get our x. And so we get x plus 1/3 plus 1 equals 3. And we have to be really careful of the arithmetic. We have a fraction involved. So x equals 5/3. And I think I tucked the solution way up here at the top. Yeah, 5/3, 1/3, and 1. Now you see it takes a bit of work, but it's doable. So let's look. How many solutions should we expect? Well, for a system of linear equations, exactly one of the following is always going to be true. One solution, infinitely many solutions, or no solutions. In both of our cases. Now, two new words. A system of linear equations is called consistent when it has at least one solution. If it has exactly one solution, those equations are independent. If it has infinitely many solutions, they are dependent. And if it has no solutions, we have an inconsistent system.